Okay, so now that we have introduced concepts of finite group, and also I said that they can all be, these finite groups can all be subgroups of the symmetric group of n objects, where it involves permutations of n objects, which we call it a symmetric group of degree n. We are now in a position to look at how these applications are looked at in molecules, which is composed of atoms, and these molecules have certain symmetries. This is what I was trying to say in the last class. I did start off saying that you can have configurations of atom in a molecule and you will have a symmetry axis. One of them is the conventional rotational axis, and depending upon what symmetry you have, if the configuration is such that it has a symmetry where by doing pi by 2 rotation you get back the same atom, like one atom goes into the place of the other atom and it looks exactly similar to the earlier configuration, then you will say that it has a 4-fold symmetry, right. 2 pi by n is the rotation. Is that clear? Or everybody is with me? So, this is also similar to your cyclic group which we were studying, where you had a generator. Sometimes people use synonymously Cn as an element, and when they write the set for the Cn group, you write identity Cn squared and go on till Cn to the power of n minus 1. So, this is, it is used as sometimes also as a generator. Okay. Besides the axis of symmetries of various rotational 2 pi by n rotations, you could also have planes of symmetry. One plane could be containing the symmetry axis, n-fold symmetry axis. Other plane could be perpendicular to the symmetry axis. Some of the notations which are followed are that sigma h is the plane which is perpendicular to the symmetry axis, and sigma v is when it contains the symmetry axis. Not all molecules will have these symmetries. Okay. So, that also you should remember. You have to look at the molecule and see what all the possible symmetries are there. If you do a sigma h, if it goes into a configuration where atoms do not go into each other, then it is not a symmetry of that molecule. Okay. So, you have to see what is the principal axis. So, the main axis of rotational symmetry with the higher value of n is what is called as a principal axis. So, you have to see what is the principal axis symmetry. We saw this in the last class. I showed you a water molecule, I showed you ammonia molecule. You know, looking at it, that the rotational axis has to be 3-fold for ammonia molecule, where the axis has to pass through the nitrogen, and similarly in the hydrogen, in the water molecule, the axis has to pass through the hydrogen, and you have this oxygen, so that you have this rotation which is 180-degree rotation, right. So, you can recall pictorially what is happening, whatever I have been saying as a group theory tool with elements, generators. Now, you can see it as an elementary operation which you do in this configuration of atom which constitute a molecule. So, this is basically a rotoreflection. So, sometimes the molecule will not have a pure rotational axis, it will not have a pure mirror plane symmetry, but you could do something like do a rotation and then a reflection, and that combination may be a symmetry. I will show you a couple of things so that you understand. It is called rotoreflection. And there could also be diagonal planes. So, let me just go again on this, since it is. So, the mirror planes can be of types like one, as I said, mirror plane could be perpendicular to the principal axis of rotation, okay. And then there could be another mirror plane where you have the mirror plane being containing the axis of rotation. So, principal axis means the one whose rotation angle 2 pi by n, the n-fold axis, n which is the maximum is what we call it as the principal axis. Sometimes you know, you look at a molecule, it will have a two-fold axis symmetry, it will have a three-fold axis symmetry, it will have a four-fold axis symmetry. If you have that, then the principal axis is only the four-fold axis. Okay. So, the others are all not the principal axis symmetry. Okay. And if the sigma v plane which you are going to consider contains that principal axis, then you call it to be, the notation is sigma subscript v, and that is a plane of symmetry. For example, in these examples which I talked, the principal axis is only the two-fold axis, rotation by 2 pi by 2. Okay. If you look at this ammonia molecule, you can see that the principal axis is a 2 pi by 3 rotation. Okay. So, here you have only one axis, so it is not very, you do not need to worry so much about principal axis, but if you see the cube, okay, the cube has four-fold axis rotation. How many of them are there? There will be 3 of them, right. Along this axis, if you do a rotation about this axis, the cube remains, the configuration remains the same, but there can be 3 axes, right, one this way and then the other face, right. There could also be a three-fold rotation axis. So, in this case you will say the principal axis is a four-fold axis. If suppose the atoms are placed on a cube which constitutes a molecule which has this cubic symmetry, then the principal axis of rotational symmetry for the molecule which has this cubic symmetry is four-fold axis. It is a notation. So, typically when we look at molecules, we start looking at what are the basic axis of symmetry, planes of symmetry for the molecule. Those are the elementary operations. It is exactly like generators of your group which we were studying. And then you start composing all possibilities of these axes of symmetry and planes of symmetry, and you start generating the finite set and they form a group. Okay. So, this is the group which is group symmetry associated with the molecule which is constituting that configuration of atoms, for example ammonia molecule. Okay. These notations, as he said already, these notations are important only when you have a principal axis of symmetry, otherwise you just call it as a mirror plane sigma. Okay. Okay, so there are these additional mirror planes which is called diagonal mirror planes. If you have this dihedral group I said, but then we will see how to see the dihedral group in the molecular language, in the molecular structure language, and in those cases you can start seeing if there is a diagonal bisection which you find, and then you start talking about diagonal mirrors. So, we will see one or few examples so that you start understanding this notation. Okay. Just to say a few lines about rotoreflection. Rotoreflection, the symbol is S subscript n. What it means is that rotate about an n-fold axis, that means you do a 2 pi by n rotation followed by a reflection about the plane of the symmetry. Okay. So, the plane of the symmetry is perpendicular to the axis of rotation. What is that plane called? Sigma h. Okay. Sigma h, if it is, this is the axis of rotation, the plane is perpendicular to the axis of rotation, we call that plane to be a sigma h plane. Subscript 1 means you do no rotation, right, you do not do rotation at all. So, you have an element, rotation about n-fold axis is identity operation, and then you do a reflection about the plane, which means this element goes here below. Are you all with me? This is what is rotoreflection S1. It is nothing but it is just the mirror symmetry, right. S1 is isomorphic to sigma h and sigma h is made of element identity and the mirror transformation. Okay. S1 is what? It is a rotoreflection. Rotoreflection, and this 1 denotes rotation by 2 pi by 1, which is 2 pi rotation, and then you do a reflection on a plane which is perpendicular to the axis. Is that clear? And S1 is nothing but your just the mirror plane symmetry, and that also forms a order 2 trivial group. As I said, generators are sometimes written as the group element also. The group is also denoted by the generator. Okay, like for example, Cn, you can write it as E Cn, Cn squared. Okay. This is the way of writing it. So, let us look at S2. What happens to S2? S2, you have to do a rotation by 2 pi by 2, which is 180 degree rotation, right. You take this atom, do a 180 degree rotation, but that is not rotoreflection. You have to do a reflection about this plane and you get this point. Okay. So, is that right? Is it clear to you from the picture? So, this is nothing but your inversion group. Given an atom, you have a, by an inversion, suppose you have a vector, let us take a sphere. If you take a point here, the point completely diametrically opposite to it can be seen as an inversion about the center, right. You can see it as an inversion about the center. This is exactly what is happening. This S2 is a rotoreflection with rotation by 180 degrees and then a reflection. That symmetry group is isomorphic to an inversion group which is denoted as C subscript I. Do not confuse this I with N. This is made of identity and an inversion. So, I squared is also E, but I is an inversion. So, given a vector R, under inversion you go to minus R, that is what is the inversion. Clear? So, the rotoreflection symmetries are seen in some atoms, and you have to remember that this is also a 2 element group. S2 is not isomorphic to C2. So, you have S2 which involves inversion, C2 which involves pure rotations. Okay. So, there are a lot of distinctions which you have to see from these groups. Okay. So, now that I have given you some flavor of how the atoms can be distributed in a molecule which has some kind of a symmetry structure, which you can call it as a molecular symmetry, we will start looking at from the group theory point of view what we studied earlier. The set containing elementary operations. Elementary operations could be rotation about principal axis, it could be reflection about the planes of symmetry. Okay. So, those are elementary operations, and then you can also compose these elementary operations. You can do a rotation and then a reflection if reflection is also symmetry of the system. So, you start writing that set. Okay. That is what I did for the water molecule, right. So, when I took the water molecule, I saw it has a C2 symmetry, I saw it had a sigma V symmetry. C2 is nothing but identity and C2, sigma V is nothing but identity and sigma V. These are the elementary operations. you can compose these elementary operations and write a set which you call it as C2V, which is E C2 sigma V C2 sigma V. And it is nothing but a direct product of it is a direct product group for an example. Okay. So, this set which you are constructing is a finite group, and this finite group which you, this is for example a molecule I took, water molecule, but you can write for many molecules different group symmetries, and this we call it as a point group. In the context of molecules, we call this as a point group, which is made up of elementary operations and then composing elementary operations. And that set should satisfy those properties of the 4 axioms of the group. Okay. And each of these group which you are going to find will always be a subset of some symmetry group. What is that theorem? Cayley's theorem. Okay. So, all these point groups, which, why is it called point group? Anybody can know why the name point group came in the context of molecular symmetries? At least one point in the molecule through which the principal axis goes, right. Take an ammonia molecule. Nitrogen atom is not moved by any of the transformations. Okay. Similarly, the oxygen atom is not moved by the C2 or a C. At least one atom will remain untouched. That is why they got this name point group. At least one point in the configuration of an atom is going to be remaining fixed under all the elements of the group. Okay. Correct. Yeah, good. So, the cube and other symmetries are a little more than the point group symmetries which I am looking at it. So, there if you think there is a atom at the center of the cube, then you can think that that point is not untouched. So, if you look at it as a methane molecule, like for example, if you take a methane molecule, if you put the axis through the carbon, that carbon remains invariant. So, in the context of these molecular, so cube was just a simple example to show you that you can look at it this way, but in general there will be always a point which I do not need to touch by any of these transformations. The center point of the cube will not be touched. Whether there is an atom at the center point is your question, but I could have put an atom there and still the cubic symmetry will be still there, right. So, that is what I mean by this. Yeah.
For a given photoreflection group, is it fair to say that we can say that it's we can map it to some other rotation group?
That is a good point. See, first of all, pure rotations are completely different from reflections. You know why, right? If you take a plane and do a rotation, the determinant of these matrices, when you write it, you can never make it negative, right. But when you do a reflection, the determinant can become negative. You can never transform pure rotations to become improper transformations. So, rotoreflection can never be made into look like a CN. If at all you want to make rotoreflection to look at some other point group, it should have an improper transformation component in it.
Can we find a plane where it's purely a reflection?
purely a
reflection.
S1 for example is a purely a reflection. Rotoreflection S1,
But is it generally true?
it is not generally true. It will have, we will see some more examples and then you can, I will give more problems and then we can see all those things, okay. So, but as of now you should distinguish a pure rotation which is about an axis of rotation is very different from the reflection planes, inversion symmetry, point, okay. They are all improper transmissions. Is that clear? You can never make a composition of rotations to look like a reflection, that is all I am trying to say. Whatever composition of rotations you take, it will never give you, it is clear, no? If you do C2 and then a C2 square, you are not going to get sigma V at all. Sigma V is a distinct generator and these two composed, one will be this element, you can call it to be an improper transformation, because C2 is a proper transformation or proper rotation, sigma V is a reflection, combining a reflection with a proper rotation is an improper transformation. Okay. So, the number of elements in the point group, I have kind of given you a flavor with some examples like ammonia molecule and water molecule, that you do see that the number of elements which we write by looking at the symmetry of a molecule, I can construct this and the number of elements will be finite and there will be subgroups of symmetric group of degree n, okay.